Hi, welcome to Organic Chemistry. In this presentation, we're going to look at our final spectral technique, mass spectrometry, often known as just mass spec or MS. Now, mass spec is not based on the same principles as found in various spectroscopy techniques that we've seen before, like IR, NMR, and UV-Vis, because in those techniques we were looking at the interaction of light with molecules to figure out something about how those molecules responded to different energies of light. But like those, even though we have a different physical principle involved, we're going to get some graphical data which we're going to interpret to learn about the structure of a molecule. So we generally think of this as following along with those. But what is this different technique that I've alluded to, this different physical principle? In mass spectrometry, there's essentially four parts. There's something called an ionization chamber, there's a curved flight tube, there's a detector, and then at the corner, the elbow of that curved flight tube, there's a magnet. Let's start out by figuring out what each of these things is about, and then we'll see how these tell us about a molecule. Let's start with the ionization chamber. All types of mass spec start out with some molecule over here in the ionization chamber that's turned into an ion. There are different techniques, but we're going to focus on something called electron impact ionization. In other settings, you might hear about fast atom bombardment or other ways of turning molecules into ions. Some of those are particularly important for large biomolecules, for instance, like proteins. But we're going to look at EI, electron impact, which is probably the most commonly used one for small organic molecules. So in electron impact ionization, what happens is you start with a molecule and you zap it. It gets hit with a beam of high energy electrons. And when one of those electrons comes along and hits, in this example case, ethane, it can knock an electron out, pretty much like a game of pool. That electron, it repels electrons, and so when it comes flying through this ethane, it could just knock an electron away to make something called a radical cation. It's positively charged because if this electron knocks one of these electrons out, now we've got one fewer electrons, so we'll have a positively charged species. And it's a radical because somewhere there's an odd number of electrons, because we started with a total, in this case, of 2, 4, 6, 8, 10, 12, 14 valence electrons, and here we would have only 13 valence electrons. I'm not saying here which exactly electron was knocked out. But in fact, which electron is knocked out? Well, it could have been one of the ones from this carbon-carbon pi bond, or it could have been one of the electrons from any of the carbon-hydrogen pi bonds. So we could have something like this or something like this, where one of the electrons has been lost, and I'm symbolizing a carbon-hydrogen where there's only one electron shared between the two with a dot and a plus, because there's going to be a positive charge somehow distributed between this. And of course, if a covalent bond involves a shared pair of electrons, if there's only one electron shared, that's not going to be as strong, it's not going to be as stable. And so this thing can fall apart. This carbon-hydrogen bond could break apart, but it could break apart in one of two ways. The electron could end up with carbon, in which case we'd make a carbon-centered radical. A radical is something with an odd number of electrons. But then that hydrogen goes away with no electrons. That's an H+. On the other hand, the hydrogen could go away with the electron, in which case we're left with a carbocation. On the other hand, if we took an electron in this initial step away from the carbon-carbon sigma bond, pardon me, excuse me, I hope that didn't knock your ears off. If we take an electron away from this carbon-carbon single bond, if that falls apart, the electron's going to go with one of the carbons, so we're going to get a methyl radical, and the other carbon is going to be left as a carbocation. Now, in the ionization chamber, you start with ethane. and you hit it with a high-energy fragment of electrons, a high-energy stream of electrons. And after that happens, all of these things are found in the ionization chamber. The ionization chamber has some of this. This is all in the gas phase, by the way. Various electrons. There's various radical species, and there's various positively charged species and negatively charged electrons. But the important things are the carbocations. Or sorry, I should just say the cations, because they're not all carbocation. The positively charged species. It turns out in this example, after this is excited and starts to fall apart, within that, large number of molecules, say 6.02 times 10 to the 23rd, well, there wouldn't be a mole, but still 6.02 times 10 to the 20th, because you just squirt a little tiny amount into the ionization chamber. You've still got a lot of each of these possibilities. Some of this, some of this ethane radical cation, some protons, some ethyl carbocation, and some methyl carbocation. And one thing about these is these have different masses. That's going to be important to us. A proton just weighs 1 atomic mass unit, methyl 15, ethyl 29, and the parent minus 1 electron weighs the same thing as the parent, right? Because ethane weighs 30 atomic mass units. And if you take away an electron, you haven't really changed the mass. These positively charged ions, as seen on the previous slide, are shot out of the ionization chamber because there's a series of negatively charged plates around a small hole which essentially attract the positively charged species and kind of suck them into the next portion, the flight tube. And they're accelerated down this flight tube. Now, an object in motion stays in motion unless acted upon by some force. So if something's shot in a straight line, it's just going to shoot down this tube and eventually run into the wall. By the way, I should note that this tube is under a high vacuum, so there's not other molecules in the tube for this to run in, for these ions to run into. So they'll just basically shoot into a straight line, but if they run into a wall, game's over. And that's the story. But notice we've also got this tunable magnet. We can turn on a magnetic field. And if we do so, that's going to cause these molecules to start turning, or these ions to start turning. Because when a charged particle moves through a magnetic field, it's going to feel a force acting upon it. Now, if I rolled 3 balls across the table, a ping pong ball, a tennis ball, and a bowling ball, and I blew lightly across a breeze across that table, well, that's going to put a force on those. But the smaller the mass, the less the momentum, the more things will move in response to that breeze. So the tennis ball, if there was just a light breeze blowing across the table, would probably turn quite a bit, and the bowling ball, really not much at all. The same thing happens here. If there is a weak magnetic field, light particles will turn a lot in response to that. Mediums, not so much. Heavy particles, hardly at all. But at a weak magnetic field, the very light particles will turn just enough, they'll go 90 degrees, and they'll hit this detector. Okay. But this field is tunable. This magnetic field can be increased. And so we can get to a medium magnetic field. Now, if we increase the magnetic field, the amount of force acting upon charged particles is increased. The very light particle will turn even more. It'll go something less than 90 degrees. And so it'll end up turning too much and crashing to this inside wall. Medium particle would end up turning and hitting the detector. The heavy particle would turn, but it's still not getting enough force, so it's not going to turn enough, so it'll crash into the outside wall. It's like in a NASCAR race or something where, if you don't turn enough, you hit the wall. If you turn too much, you hit this inside wall and crash. But if you turn just the right amount, you end up going on to the detector. But we're going to keep increasing the magnetic field, and if we get to a strong magnetic field, now the light particles and the medium particles are going to turn so much that they hit the inside wall, but the heavy particles are going to hit the detector. The result is that we're going to see a spectrum. We're going to see something where along this axis we've got essentially the increasing magnetic strength of that tunable electromagnet. And that's going to correspond to mass, because the less magnetic strength, the lighter particles will hit the detector, and at heavier magnetic strength, the heavier particles will hit the detector. And so we're going to see this thing. The y-axis is essentially the strength of the signal hitting the detector. So there could be nothing or there could be something. And notice that some of these signals are bigger than other signals. And that's just because more particles hit. So here, for instance, is the mass spec for isopentane, also known as 2-methylbutane. Now, I want to point out a few things about this spectrum. First thing that's of interest to us is this signal here at 72. Now, if we figured out the molecular weight of isopentane, it's 72. And so it makes sense that we should see a signal at that, because if we just took isopentane and removed one electron, we'd make a radical cation, and so there should be some molecules, or some fragments, or some pieces that weigh 72. Now I'm going to leave aside some of these others for the moment. This is called the molecular ion. The molecular ion is the heaviest peak, and I'm going to put a little asterisk on that because I'm going to come back to, you might notice that there's a little blip at 73. But the heaviest peak, in quotes, and that's just the molecule itself, and that's called the molecular ion, or the M+. But notice there's a lot of other peaks. For instance, there's one at 71. Well, how could we get something that weighs 71 out of isopentane that weighs 72? Well, what if we just lost a hydrogen? So what if we had this fragment, which basically came from breaking a CH bond and making a carbocation? That would be something at 71, and we do see that. But we'll notice that there's some other peaks as well. There's nothing at, 70 or 69 or 68, but there is here at 57. Well, what weighs 57? We start with 72. 57 is 15 less. Well, if we broke just a carbon-carbon bond, so we got rid of a CH3, that's worth 15, because carbon's 12 and each of our 3 hydrogens is worth 1. So M minus 15 is 57, and that's this signal. Here we see a signal at 43. That's what we get if we broke the carbon-carbon bond that was here, and we get this fragment. That's called the base peak because it's the biggest signal. The base peak represents the most common fragmentation pattern. That is, more of the molecules break down that way than any other way. And you look at this gives us a secondary carbocation, and that's, a reasonable thing to make. What you'll find is in the mass spec, you'll make more of the more stable carbocations. And so, you'll make this more often. And it kind of depends on some other things too, what bonds are stronger and what are weaker. Weaker bonds are more likely to break. This piece weighs 29, and that's what comes from when we broke that carbon-carbon bond, the other half, because 29 is an ethyl, and there's also a piece down here for a methyl part. So notice a lot of these peaks can be characterized by simple, if I break a particular bond, I'm going to get pieces of these different masses. Now there's other peaks I didn't highlight. Some of those involve breaking more than one bond, like if I broke a bond and then I also lost a couple of hydrogens or something like that. But one peak that's kind of interesting. We said that isopentane weighs 72. But what's that little peak there at 73? Now this takes us back to the periodic table, because we got 72 by saying, well, C5H12. Yeah, C5H12. So each carbon weighs 12 and each hydrogen weighs 1. That gives us 72. But you know what? If you look at the periodic table, it says carbon weighs 12.01. But you know what? There aren't actually any actual carbon atoms that weigh 12.01. Instead, that's a weighted average. 99% of all carbons weigh 12, and 1% weigh 13. This 12.01 that we see as the atomic mass is just, if we have a lot of molecules, like if you go to the balance and you weigh out some compound, you've got like 6.02 times 10 to the 23rd carbons. Well, you can just do statistics, and based on, assuming that 99% of them weigh 12 and 1% of them weigh 13, you could say on average they weigh 12.01. But when we're looking at mass spec, we're seeing blips not for collections of molecules, but for individual molecules. And if my carbons weigh 12 and my hydrogens weigh 1, I'll get a molecule of mass 12. But that happens 99% of the time. But 1% of the time, a carbon will weigh 13. And so if 4 of my carbons weigh 12 and 1 of my carbon weighs 13, and 12, my hydrogens weigh 1, that'll give me something that weighs 1 more. And notice we see a very small blip here. That's 1 heavier than 72. That's at 73. This is called the M+1 peak. The M+1 peak represents the small number of molecules that happen when you get the heavier isotope of carbon. With high-resolution mass spec, you can actually quantify the relative sizes of these, and that can be very useful. But for our purposes, we're just going to recognize that that little tiny blip represents the presence of some molecules with carbon-13. But there are a couple of other elements that have important isotopes in the mass spec. Bromine, and let me step back and just say organic chemistry, we're mostly concerned about carbon, hydrogen, oxygen, nitrogen. And for those things, hydrogen, oxygen, nitrogen, pretty much we're going to be dealing with just the one isotope. About 1% of all carbons weigh 13. And the halogens. And 2 of the halogens are interesting in this aspect. Bromine, if you look at the periodic table, has an atomic mass of 79.9. But if you were to look at individual bromine atoms, about 50% of them weigh 79, and about 50% of them weigh 81. So this 79.9 is really the weighted average of having a half and half mixture of 79 and 81. If I had bromobenzene, if I had 6 carbons that each weighed 12, and my hydrogens that each weighed 1, and a bromine that weighs 79, that would add up to 156. If I had bromobenzene, where I had 6 carbon 12s and a bromine 81, that would weigh 158. And in the mass spec, notice that I see 2 signals, the M and what's called the M+2, the molecular ion for the smaller isotope of bromine, and the molecular ion for the heavier isotope, that are of roughly equal size, 2 atomic mass units apart. Notice there's also smaller blips here for M+1 and M+3. Those are for the presence of carbon-13. So if you've got 5 carbon-12s, 1 carbon-13, and a bromine 79, you'll get the M+1. If you have 5 carbon-12s, 1 carbon-13, and the bromine 81, you get this M+3. Another element that's interesting is chlorine. Chlorine, in the periodic table, the atomic mass is 35.45. But that's really a weighted average again, because about 3/4 of all chlorines weigh 35, and about 1/4 weigh 37. And so the weighted average is 35.45. But the way this manifests itself in mass spec is that you'll see an M and an M+2 peak that are roughly 3-to-1 ratio. So for chlorobenzene, if you've got 6 carbon-12s and a chlorine 35, you'll have a mass of 112. That's this peak. Of course, if you have 5 carbon-12s and 1 carbon-13 and a chlorine 35, and the 5 hydrogens, you'll get a mass of 113. That's that little peak in between. But if you have 6 carbon-12s and a chlorine 37, you'll get 114. 5 carbon-12s, carbon-13, and a chlorine 37 gives this little peak at 115. But the thing I want to focus on is if you see 2 signals, an M and an M+2, where the M plus 2 is roughly a third the height of the M, well, that indicates the presence of a chlorine. So another thing that you can get out of mass spec. We saw that mass spec you can observe the molecular weight. We saw that in mass spec you could look at you could look at fragments, particularly the base peak, are different ways that the molecule breaks down. Here we see that sometimes you can see particular elements like bromine and chlorine, and you can even see the presence of carbon, though that's a little less enlightening, by these M plus peaks. Alright, let's just look at a couple of molecules. I won't go through all these molecules in great detail, I just want to point out a couple of features. Here's the mass spec for hexane. Hexane is C6H14. If you had all carbon 12s, C6H14 would weigh 86. And here we see the molecular ion peak. That's for 6 times 12 plus 14. You also see a little blip here. That's for C6H14, where one of the carbons is carbon 13. That's the M plus 1 peak. I just want to look at this peak here, because that's our base peak. That peak weighs 57. 86 and 57 are 29 atomic mass units apart. How can we get to something that weighs 29 less? Well, if I was to break this carbon-carbon bond, okay, I'd be left with a fragment that was made, so I got rid of 2 carbons and 5 hydrogens. I'm going to be left with something that has 4 carbons and 2, 4, 6, 9 hydrogens. And that turns out to weigh 57. So our base peak here, the most common fragment, comes from breaking a particular carbon-carbon bond. Now we could look at other fragments, like this one at 71. Well, that's 86 minus 15, and 15 is a CH3. So if I broke this bond, I'd lose 1 carbon and 3 hydrogens, so I'd get something that weighed 15 less. And that's this peak here at 51, or 71, I'm sorry. This peak here at 43, I could account for by breaking this bond, because if I broke that bond, I'd get a molecule that was exactly half, or I shouldn't say a molecule, I should say a fragment of a molecule, that was exactly half the mass of our initial molecular weight, and that would be 43. This here at 29 is breaking this and looking at this fragment, and there's a tiny little blip there at 15 for breaking one of these carbon-carbon bonds and looking at that fragment. Alright, let's look at 2-chloropropane. C3H7Cl, if we have all carbon 12s and chlorine 35, has a mass of 78. And that's this signal here. But if we've got chlorine 37, we get an M plus 2 peak. That's at 80. That's this signal here. And notice these have roughly a 3-to-1 ratio. Now, if this is our M at 78, our molecular ion, this here at 63 is 15 less. Now, how could we get something that's 15 less? Well, if we just broke a carbon-carbon bond, we're going to form a little piece that's 15. We can see a little blip for that here. But then we're going to see a piece that weighs 63. That's if we have 2 carbon 12s and a chlorine 35. But of course, if one of these 2 carbons was if these carbons were carbon 12, but this was chlorine 37, we'd get something that didn't weigh 63, but instead weighed 65. So notice we see a peak at 63 and a peak at 65, again, roughly 3-to-1 ratio. What if we broke the carbon-chlorine bond? Well, if we broke that, we'd get a fragment that had 3 carbons and 7 hydrogens, and 3 times 12 is 36, plus 7 is 43, and look what our most common fragment is, this one here. And so our base peak, the largest peak, could be explained by just simply breaking the carbon-chlorine bond and looking at the 3-carbon fragment that was left. I'm just going to look at a couple more really quickly. Here's 3,3-dimethyl-2-butanone, and the molecular weight of that, of C6H12O, is 100. So here we see the molecular ion peak, and there's an M plus 1 peak. But I just want to look at the base peak here. let's see, that's at 57. How could we get to 57 from 100? Well, 100 minus 43. And what's 43? Well, if I was to break this bond here, this carbon-carbon bond, I've got a CH3, a C, and an O. So that's 2 carbons, that's 24. 2 times 12 is 24, plus oxygen, 16, that's 40, plus 3 hydrogens, that's 43. So if I broke this bond, I lost 43. I'm going to get something that weighs 57. That's the base peak. By the way, here's a signal at 43 for this piece. We could also look at just losing 15. That's this peak here. So if we were to break one of these and make a plus charge here, that would give us a little blip here, and we could explain some of these others as well. But again, we can at least rationalize the molecular ion peak and the base peak and some of the other major peaks as coming from this molecule. And one more, isopropyl propionate. The molecular ion peak in this case actually weighs 1, 2, 3, 4, 5, 6. 6 times 12 is 72, plus 32 is 104, plus 109, should have figured this out before, 112, 115, 116. It's right here. It's this little tiny blip. You can hardly see it. Sometimes the molecular ion peak is hard to see, but if you look really close, you can see that the molecular ion is right there. The next peak down is minus 15, and that makes sense. If I was to break this bond or this bond, I'd get a plus charge here, or this bond, but it turns out it'd be more reasonable to put a plus charge here for the sake of stabilization. But let's look at this peak here at 57. If I was to break here, I'd get something that had 3 carbons and an oxygen. So 36 plus 16 is 42, plus 1, 2, 3, 4, 5. That would weigh 57. So our base peak comes from breaking this right here, and that'll give me this. I could go through and explain some of these others, but let's just focus on the base peak. Now, I don't expect to get a lot of information from mass spec. If real experts on mass spec can actually go through and look at the mass spec and figure out a lot about the structure of the molecule. We're generally going to use mass spec to figure out the molecular weight if we don't have the formula. Because if we don't have the formula, you got to start somewhere, and the molecular weight is a good place to start in figuring out the molecular formula. We also should be able to rationalize parts of the mass spec, particularly the base peak, if we've got a structure to work with. So oftentimes mass spec can be a check on figuring out the structure. All right, that's our last spectral technique. If you go to the handouts, there's also a handout called Combined Spectral Problems. That's just a lot of practice problems, so I'm not going to go through that as a recorded lecture, but I would highly, because there's an answer key with that, I would highly recommend you do as much practice as you can. All right, look forward to seeing you. Thanks, bye.